So in that last video that you watched, you saw one example of how atoms can achieve the octet rule or obey the octet rule. And that is by one atom actually giving an electron to another. All right, that makes one of them positive, one of them negative, and then they want to stick to each other because of that difference in charges. All right, and that makes what's called an ionic bond. All right, the thing is that there's another way that atoms can achieve obeying the octet rule that has nothing to do with losing or gaining electrons. It actually has to do with electrons sharing electrons, with atoms sharing electrons. So let's see an example of that. So let's take a look at this atom right here. This would be a neutral hydrogen atom. All right, it's got one proton and one electron. All right, this guy right here is neutral fluorine. All right, so in terms of the octet rule, we could see that hydrogen would want to gain one electron. All right, on the periodic table, its closest noble gas is helium right over here. And helium has 2 electrons. That's why it wants to gain 1 electron. All right, fluorine is closest to neon. It also wants to gain an electron. All right, so we couldn't do the same thing with these 2 atoms like we did up here. All right, because both of them want to do the same thing, to gain electrons. So instead of one losing an electron, essentially what's going to happen is that they're going to share electrons. All right, and this is a little bit oversimplified, but it's a way that you can think about this. All right, and so this is going to make these guys are going to share these electrons, and you can see over here where the electrons originally came from. All right, and when this sharing occurs, when this sharing right here occurs, that's what we call a covalent bond. So this is a covalently bound hydrogen. And note, if we just kind of take a look at, I'm going to circle, put a circle around this right here. If I just put a circle around that atom right there, you can see it now possesses, that atom that's circled now possesses the same number of valence electrons as helium would. It owns 2 now, but it does that by sharing electrons. All right, let me erase that. All right, so over here we've got that fluorine, and this is a covalent bound fluorine. All right, so focusing on the hydrogen right here, it's got the same number of valence electrons as helium, which is 2. But if we do that same little trick with fluorine right here, you would see that it has the exact same number of electrons as neon. All right, and which is 8. All right, and so by the way, one thing that might be confusing, we talked about, call this thing the octet rule, and it makes sense that octet rule might have something to do with the number 8. All right, generally it does. For most atoms, it means it wants to have 8 valence electrons, just like fluorine does here. But note that with hydrogen, there's an exception. All right, it only wants to have 2. So you would still say it's obeying the octet rule, even though it doesn't have 8 electrons. All right, and that's because the octet rule just means that it wants to have the same number as the closest noble gas. A simplified way of saying that is that it wants to have a full outer valence shell. All right, and so for hydrogen to have a full outer layer, it wants to have 2 electrons. Okay, so I've just summed those 2 situations up right here. So the 2 ways that they can obey the octet rule, one is by transferring electrons. All right, and that means that they're going to eventually be held together by what's called electrostatic forces, which is just a way of saying the attraction of I got that mixed up. The repulsion of like charges and the attraction of opposite charges. All right, if you've ever played with little refrigerator magnets, you've probably noticed that in certain ways they push apart, but in other ways they want to cling together. And you can kind of think of that as an analogy for what's going on here. All right, so that attraction is going to cause what are called ionic bonds, and this is the type of bond that holds ionic compounds together. And by far the most famous example of an ionic compound is sodium chloride, NaCl, all right, common table salt. All right. The other example was one where they shared electrons to make covalently bound atoms. All right. And what holds them together is in the sharing, you're going to have electrons surrounding positively charged nuclei. All right. And it's this balance of the negatively charged electrons with the positively charged nuclei that create essentially the glue that holds them together. All right. So a covalent bond can be thought of as essentially like a cloud comprised of shared electrons. All right. The most common example of a covalent, or one of the most famous examples, would just be water. All right. And if I were to draw, and we'll talk about these structures a little bit more in this unit, but the bonds are represented by these lines right here. So these are covalent bonds. And if I were to draw this as a formula, it would just be H2O. All right. So the forces that hold the oxygen and the hydrogen together in water are different than what holds the sodium and the chlorine. All right. Because this is an ionic bond, but this is a covalent bond right here. So the first type of compound that we're going to talk about are ionic compounds. All right. So in order to think about how atoms would come together to make ionic compounds, first we need to determine how to determine the charge on atoms. All right. So there's even though we could logically figure out how what the charge would be through saying, all right, would some things like to gain or lose electrons? Once you get used to this, you'll realize you can figure out what the charge is just by looking at the periodic table and figuring it out by its position. All right, so here's the periodic table. All right, so if you look at the periodic table right here, you'll see that in this column right here, everything in that group of the periodic table, which is the alkali metals, when they make ions, they're going to tend to have a +1 charge. All right, everything in this column will have +2. All right, over here, we've got -1, -2, -3. All right. So for example, this would be nitrogen right here, which would have, as an ion, it's going to have a -3 charge. All right. The noble gases, which are the elements in this family right here, they don't make ions. And the reason that they don't make ions is they already have a full valence shell. All right. So a way of rationalizing this is to think about, like, if we had a neutral beryllium atom, for example. All right. It wants to have the same number of electrons as helium right here. All right. So what does beryllium right here, if it were neutral, what would it want to do in order to become like helium? It would want to lose 2 electrons, and when that happens, that's going to give it a +2 charge. All right, and you can do the same thing on this side. Chlorine would want to become like argon, so neutral chlorine would want to gain 1 electron, and when it gains 1 electron, it would make it chlorine minus. All right. So the thing is, even though we can understand the reason for why they want to have these charges, in practice, if you want to know what's the charge on a chlorine ion, for example, all you have to do is look at its position on the periodic table. And if it's in this column right here, it's going to have a -1 charge. All right. We'll talk a little bit later about what charges the atoms in the center of the periodic table will have. But for right now, this right here will suffice. All right. One little example, a little bit of an outlier that also follows this rule is going to be aluminum right here. And that's always going to have a +3 charge. All right. And this can trick people up because it's on the right side of the periodic table. But if you think about it, if you were to take out this middle section, it would be right here, right next to magnesium. All right. So it's going to tend to want to lose 3 electrons so that it would be like neon. That's why it has that +3 charge. So if you wanted to practice this, all right, so you can pause the video for a second and try to predict what ions these atoms right here would make. All right, calcium, bromine, potassium, and nitrogen. All right, hopefully you figured out that they would make calcium +2, bromine minus, potassium plus, so that's, and nitrogen makes nitrogen -3. All right.